Hello, this is Dr. Muhammad, and this is another video under dynamics of structures. Today I'm going to talk about the forced vibration response to harmonic motion, and today I'm going to talk about the damped system. Last time we covered the undamped system, so today we are going to talk about the damped system, and I'm going to, in this video, it is going to be the first part of it. After that, I'm going to talk about another part. Okay, now let's see the next step. As you can see here, we are going to have the these are the contents of today's video, and we are going to talk about the first of all the contents of the first of all we are going to talk about the equation of motion, and we are going to talk about the general solution after that, and the graphical representation of the solution, and then the response for resonance whenever that we have omega equal to omega n, or omega, the forcing frequency, equal to omega n. And the last thing is going to be maximum deformation and phase angle. We're going to talk about the maximum deformation related to the response modification factor and the phase angle. Okay, so now let's start with the equation of motion. So let's start with the equation of motion. And in our equation of motion, we are going to put the general equation of motion that we usually use, mu double dot plus cu dot plus k u equals to p node sine omega bar t. So this is how it works for us. Okay, remember well that if we're going to talk about this equation, remember well that sometimes I use this annotation, which is omega bar. Okay, this means that the forcing frequency, this means that it is coming from the force part, okay, the right hand side. Okay, sometimes in the textbook, especially in Chopra book, you're going to find that we are, or like in the book, omega only is being used. Okay, so omega or omega bar, they are like interchangeably used, or they are like the same here. Okay, so do not be confused with this. And whenever that we mention about omega n, for example, natural period, okay, or omega d, it is related to the structure itself. This is related to the structure itself. Okay, this is only not to be confused. Again, let's go back to our equation of motion, and let's try to think more about it. Okay, first of all, we are talking about damped system, so no surprise that we can see this term is being there, which is c times u dot. Okay, so we are having this damping coefficient, and we are putting the term of damping in our equation. And in the same time, we're going to find that in the right hand side we have the forcing term, or the force that is being applied on the system. Okay, we are talking about, again, let's go back here, we are talking about forced vibration. So we're going to talk about forced vibration. This means that the right hand side is related to force. Okay, and in the same time we are talking about response to harmonic motion. So this means that we are dealing with sine omega bar t, something that is sinusoidal. Okay, this is harmonic force that is being applied, and we are talking about damped system. This means that our term here, which is this term, is going to be representing the damping term. Okay, the other two terms, this is inertia term and this is elastic force term. Okay, now let's go to the general solution of this equation. Okay, so our general solution, supposedly we are going to have two different types of solution. The first one is going to be UP, as you know, the particular solution, as we have mentioned before in the previous videos. it is going to equal, okay, C damping frequency, as you can see here, and the initial conditions, as it can be seen from A and B, and the damping ratio, in addition to omega n also, which is the natural frequency of the structure. Okay, the point is we do not know C and D. We need to know them. Actually, this can be obtained, as I said, you can obtain C and D. The derivation of them, you can find them in the textbook, but this is not our main task here. We want to go deeper into understanding of it. So I'm going to write it, and let's see after derivation what is C is all about. So this is the constant C, and we found that at the end it equals to P node over K times something that I'm going to write here. It is 1 minus omega bar over omega n squared, and in the denominator it is 1 minus omega bar over omega n squared, and the total term is going to be squared also raised to the power 2 plus another term which is 2 psi omega bar over omega n close parenthesis, and it is squared here. Let us make this take to be long. It is, we have a very long denominator here, so this is C, this is C. Let's write, okay, this is C, and we are going to find that D, let's put D here, D is going to be P node over K times, it is going to be in a very similar fashion to the first one. I think it is the same exactly. So you are not going to find, I'm going to write it here. It is the same exactly. The same denominator is going to be used. However, the numerator is going to be a little bit changed. Minus 2, and this is psi omega bar over omega n. Okay, so this is what we are going to have here. Okay, now let's go again and understand what are the factors here. We need, whenever that you look, again, remember that we need to understand what is the meaning of each coefficient. C and D. Remember, they are just constants in our particular solution. As you can see here, it's C and D. And when we are going to put and derive these C and D, the solution or the values of C and D, we found that they are having something related to these parameters, which is P node K, as you can see, P node. Okay, what is P node? P node is the amplitude of the force. Remember that we have P node here, which is the amplitude of the force. Okay, and because it's sinusoidal or harmonic, so we are having P node, the maximum force. If sine omega bar t is going to be 1, then P node is going to be the maximum amplitude of the force applied. So P node, the amplitude of the force, K, it is the stiffness of the system, right? So P node over K, it is actually what? The force over the stiffness. So it is like the maximum static amplitude, right? That's right. Then it's going to be multiplied by this huge fraction here. The first one, it is, you can see that there is something is being repeated here. Omega bar over omega n. Always repeated, right? Omega bar over omega n here. Omega bar over omega n. This means that the ratio between the forcing frequency and the natural frequency is controlling the C. Okay? And then we have the damping ratio. So there are like three, we can say like main 4 parameters. The first one is P node over K, or P node and K, and the other one is the ratio between omega bar over omega n and the damping ratio controlling C. And for D, you're going to find in a similar fashion P node over K and the same fraction, but in the numerator it's a little bit different. It is going to be minus 2 times psi times omega bar over omega n. Okay, so this is C and D that we are going to put in our equation here. Well, we are going to draw, but before this we want to add the meaning of the A and B. As we said, we're going to write them as initial conditions, and omega d. What is the omega d? As we said before, it has something to do with omega n, which is going to be omega n times the square root of 1 minus the psi squared. So let's draw here. Okay, so we need to put first that omega d equals to omega n times 1 minus psi squared. I think that already you know about this. There is a relation between omega d and omega n. This is the damped. Okay, we are talking about the damped frequency. Okay, circular frequency. We're talking about the circular frequency. And this is the undamped. This is, we call it the natural. Okay, the natural circular frequency. Okay. And then for A and B, we have another A and B, right? In the equation, if we go back, you're going to find that in the equation, we put it like this, okay? Here we have this A and B for the complementary solution, right? So A and B, they are going to be obtained from the initial condition, So I'm going to write down this. So it is from, we can say this is from the initial conditions. Okay, so we can obtain them from the initial condition, as the case for, I can write like this, as n, or as for the undamped case. So you can go to the previous video, okay, and you can find how we obtained it. Actually, I referenced it to the textbook because it is really derivation, mathematical derivation. You can find it clearly and you can understand it from the textbook. So you can find it in the 4th or the 3rd edition in Chubra book, because we are using Chubra book here. So you can find it in Chubra, okay, book, okay, the 3rd edition. It is, you're going to find it in page 71. You can like check it if you want, and you can find it there. Okay, so this is regarding A and B and WD. So now our equation is going to be like ready for the solution. Our equation of motion now, the equation EOM, it is going to have the general, okay, the general solution, okay, which is going to be what is the general solution? It is going to be 2 parts, which is part related to the complementary solution, so U complementary, okay, and we are going to give it the name of transient, as we said before, transient, and another part which is related to the particular solution, UP, which is we're going to give it the name or another title, steady state. This is the steady state, okay? And then we are going to superimpose the both together, okay? We are going to add these both solutions to get together, the complementary solution plus the particular solution, and then we're going to put it in one equation. Okay, so our equation, so let's put the general solution, okay, it is going to be like this. U of t equals, now U of t, okay, there is no C, there is no P, it is general solution. It is going to equal E raised to the power minus psi omega n t, okay, times A cosine omega d t plus B sine omega dt, close this parenthesis, plus c, we know what is the meaning of c now, sine omega bar t plus d cosine omega bar o t. I need that. So here this is, let me like erase some part here, okay, and put it in another, or erase this entire part here, okay, and make another another line. So plus, so can put it plus here, remove this plus from here, okay, plus another term which is going to be c times sine omega bar t plus d cosine omega bar t. Okay, so the first part, as we said, the first part, we have like two parts here. Let's use this. Okay, this part, okay, it is related to the complementary solution. Okay, so this is like U complementary, and this part is going to be related to the particular solution. Okay, these are the two types or the two parts of the general solution that we are going to have. As we have mentioned before, that you are going to find in this general solution, you're going to have something that is very interesting. Okay, there is something here, we call it decaying term. Decaying term. This means that which is the exponential function. This decaying term, okay, we call this decay term or decaying term, means that it is the term that is responsible for decaying this part, which is related to a cosine omega dt plus b sine omega dt. Because this part is going to vanish at the end. It is going to vanish. This part, which is the particular solution, is going to be there. This is why we call it the steady state. Because as you can see here, we are having in this omega bar, which is related to the structure, related to the like the force, the forcing frequency. So it is going to be there. C and D, even that they are having something related to the omega n and omega bar and the damping ratio, but they are going to be like constants controlling these the sinusoidal or this harmonic motion or the response of the structure, but we are going to have the sinusoidal or the harmonic steady state response based on the forcing frequency of the forcing force. Okay, that's the important part that we need to highlight. Okay, now let's go to the next part, which is related to the graphical representation, and let's see and understand more about it. Okay, now as you can see here, we are having the relation between the horizontal axis is going to be, let me highlight it here, it is t over t. Okay, you understand, of course, that t, it is the elapsed time, and capital T or T uppercase means that the natural period. Okay, and here we are having the vertical axis is going to be ut, it is the total response of the system, over u static node, which is the maximum, okay, or we can say it is the static response of the system, the static response of the system. Okay, this is actually has been drawn or sketched for the case where that we have these characteristics. Omega over omega n equal to 0.2. As I have said many times, omega here, the textbook always like having it omega. This means that omega bar. Okay, so this is the forcing frequency. So do not be confused between the two. Omega means that omega bar. Okay. And the second is the damping ratio is 5%. And we have U node, which means that the initial condition, the initial displacement or the initial displacement U node, it equals to 0.5 P node over K. And U dot at 0 means that the initial velocity, it equals to this quantity, which is omega n P node over K. So when we are going to plot this response, we are going to have this nice response in front of us. Okay, now let's go and see more. This is the total response, which is the solid line that you can see it here. It's the solid line as it goes here. This is the solid line. Okay. And the other one, which is the dashed, it is the steady state response. The steady state response. Actually, the steady state response, it has something to do with the response of the forcing motion itself. Okay, so as I have mentioned before, we have our forcing motion. It is P node, right, sine omega bar t, right? So we're going to find that it's a sine wave, for example. So we're going to find that the dashed line, it is representing this P node sine omega bar t. And whenever that we are going, the case where that this sine omega bar t is going to be 1, and we are going to divide P node over K, this would be our maximum static response, right? P node over K. P node over K, it is going to give us the maximum static response, which is going to be here. If we look here, it is going to be 1. Means that the relation between, or the ratio between the total response to the static response 1 means that here means that it's the maximum. As you can see, it is like sine wave here, and the maximum is going to be the value here, means that it equals to P node over K. Okay. So first of all, we need to understand and like take some notes, important notes about this. Okay, so let's put some notes on our graph that we are going to look here. So first note that I want you to highlight or to take care of, okay, it is going to be related to the transient, okay, the transient state, okay. So in the transient state, we are going to find, or the transient will decay, or the transient response will decay with time, and the steady state remains. Okay, so this means that if you look here, you're going to find that the transient, look here, this like this kind of zigzag going up and down. The difference between the dashed line and the solid line is high in the beginning, but whenever that the time is advancing, we're going to find that the difference is small, right? The difference is small. As you can see here, for example, look here, the difference, it is very small. However, here the difference, it was something huge, right? Why? Because actually, as we said before, the difference between the two, it is the transient state. This difference here, it is the transient that is going to vanish, to decay. It is the term that we were talking about. So here the difference is the transient. Okay, the transient. Okay, this is where this transient, if we go back to our equation here. Okay, let's go back again. So here, as we said, we are going to have our transient, which is going to be, let me show it here. Yes. So this is the decay term is in the first term, as you can see here. So this would vanish. This exponential term is going to be responsible for decaying this part. So we're going to find that in our equation, okay, this part, which is the difference between the total response and the steady state, is going to like vanish, as you can see here. okay, which is the solid line, okay, which is the solid line. Okay, so this is something that we need to put as a note. We can say that the transient response, okay, the transient response. As you know, the transient response, it is the difference between the total response and the steady state response on the graph. The transient response will decay with time, and okay, will decay with time, and the steady state okay, remains. That's the point. So whenever that we are talking about the damped system, you are going to find that what makes our response to remain is the forcing term, the steady state response. Okay, that's the first thing that we need to take care of. Okay, another thing is look to the peak values here. Look to the peak values. Let me erase this part here. Okay, okay. Where is the peak? Okay, the largest peak here. The largest peak may occur before reaching the steady state. Actually here, starting from here, we can say, starting from here, for example, on, this is the steady state. You're going to find that the system is going to make this kind of regular sine or cosine or whatever the case, right? But before that, where is the maximum response? Exactly, the maximum response here. Maximum response is going to be here. Again, what is the meaning of this value here? This means that the dynamic response ratio, or the ratio between the dynamic response to the static response, is almost like we're reaching 2 here, okay? This means the dynamic response is amplifying the static response, almost the double, almost doubling it, okay? So the maximum response is going to be reached before the system is going to go into the steady state response. That's an important issue that we need to highlight. So let's put it in another note here, which is an important note as well. Okay, so the largest peak, as we have seen from the graph, may occur before reaching the steady state. Before reaching the steady state, and this is true as we have seen from the curves, okay, or from the graph. The steady state, this is the maximum here. The steady state, we are going to find that it almost like reaching 1, right? This means that there is no amplification in the response due to the dynamic effect. Okay, very nice up till now. I hope that we are understanding how the response is going. Okay, now let's go to another part which is important for us. Now we are going to think about the response for the system when that we are having omega equal to omega n, or omega bar equal to omega n. Remember, this is coming from the force, this is coming from the system itself, okay, the system itself. So they are the same, which is, we are going to call it the resonance, okay? So this is what we want to understand. What will happen in the case where that we are having the forcing frequency equal to the system frequency. Okay, so in this case, in this section, we're going to examine the role of damping. That's an important issue. What is the role of damping? Because we have our damping here, we are having the damping ratio, right? And we have omega d as well. These are two different factors if we're going to compare with the undamped system, right? So today or now or in this video, we are going to examine how the damping is going to intervene in the response of the structure under resonance condition when the forcing frequency equal to the natural frequency of the system. And this role is going to be highlighted with the rate, okay, at which the steady state response is attained and in limiting the magnitude. So this means that damping in any system is going to be very effective and very important in terms of what? Yes, two things here. The rate at which the steady state is going to be attained and in the same time limiting the magnitude. Do you remember last time I was talking about the magnitude and the amplification due to the response of the undamped system, and we said that it is going to be like magnified to the point where there is no control over it, right? Today we are going to find that our system is going to be, as you can see here, our system is going to be controlled. There are some envelopes are going to be drawn, and we are going to find that there is some limits for the amplification. It's not going to be as the case of the undamped system, which is in the previous videos that I have explained. Okay, so now the point is, if you are going to be asked about the response for the case of resonance, you need to understand that there is a difference between the undamped system and the damped system. In the damped system, you are going to find totally different response. First of all, you are going to find an envelope that is going to control the rate at which the steady state response is going to be attained, and you are going to find some upper and lower bounds that is going to limit the response for the system, which is not found at all in our undamped system. Okay, so now let's go back. Okay, so now I want you to highlight these like keywords here because really they are very important. So the role of damping is related to the rate and the magnitude. The rate at which steady state response is attained and limiting the magnitude of the response when the forcing frequency equal to the natural frequency. Well, the point is, let me erase this part, okay, here, and then the point is, what is the general solution for us? What is the equation that is going to form or that is going to be controlling and governing the response? This is the equation, okay? U of t is going to be U static node. We understand well what is U static node, okay? P node over K, okay? P node over K times 1 over the damping ratio, the decay term as it is, e to the power minus psi omega nt. We call this the decay term. Then there is like parentheses here, and we have something sinusoidal. As you can see, cosine and sine, they are added together, right? And you're going to find inside there is omega d and omega d. The damping frequency is going to be there, and then we have t, which is changing with time. And here we are having the psi over 1 over the radical of 1 minus the psi squared minus cosine omega nt. So we are having omega n here. We are having omega n here. So what is the point that we want to highlight here? Take care that we have, remember, decaying term, okay? The decaying term, but the decaying term is going to be also is going to be controlled with the outer side term here, which is related to the static or the maximum static amplitude and the damping ratio as well. Okay, so you cannot find that T is not outside as before. Okay, T in the undamped system, do you remember in the equation of the undamped system, we found T all of a sudden comes out of the cosine and sine. It was outside of them. So it was making a great deal of a problem because, as we said, the response is going to be like amplified without controlling. But here it is very good for us to find that we have the t, okay, always inside cosine or sine. So that makes it very easy for us to go with this. The amplitude is not going to be augmented or to be amplified in uncontrolled way. And another thing, we have the decay term. The decay term that is going to control this. Okay, now let's plot what we have done here into a plot that we can understand it well. So as you can see here, we are going to have, I'm going to compare always with the response of the case where that we are in the undamped system. So let me first highlight that we are in the damped system here. This is the general look of how the structure is going to respond. Look here, this is the undamped system. This is, look how the structure is going to respond. Totally different. As you can see here, it is the amplification is going linear with t. However, here, the amplification is going to be controlled, as you can see it here. Okay, so this system that we have plotted, let me downsize this here a little bit. Yes, here. So we are having here, first of all, the system is going to have the envelope curves, that is the dashed lines here, as you can see, envelope. Our lower and upper envelopes, they are going to envelope the response. And you are going to find that the steady state is going to be attained, as you can see here, it is going to be attained almost from here. We're going to find that the steady state is going to be always there. It is going to be attained after, can you imagine here, for our case, it is for the system with damping ratio 0.05, and of course sinusoidal force is being applied, and the frequency or the forcing frequency, of course, it equals to the frequency, natural frequency of the system, and the initial condition, it was as you can see, 0. The initial displacement and initial velocity, they are both equal to 0. What is happening here? You are going to find that yes, we are being controlled. The response is being controlled. Okay, the vertical axis as it is, the total response over the static response, and you are going to find that there is bounds, upper and lower bounds here, upper and lower bounds, 1 over 2 psi, 1 over 2 psi, upper and lower. They are limiting the amplitude to be 10. Okay, go here to the undamped system. Look here. After if we are going to deal with the system with omega equal to omega n and with the same initial conditions, okay, but this is undamped system. Look at the envelope curve, envelope curve, and look how it goes here. We are reaching, look, 30, and it's not stoppable here. It is going to be more and more, right? At even 10 ratio between t over tn. Here we have at 10 almost, we are obtaining only 10 times the maximum static amplitude. Okay, so we need to understand this big difference between the two. It will help us a lot in understanding that if we could have a damped system, it is the decay term is going to control, and we are going to have 1 over 2 times psi is going to be our upper and lower bounds, and we are going to attain the steady state okay, amplitude and response after several cycles. So the system will not go and amplify, or the response is not going to be augmented after certain number of cycles. If we compare it with the undamped system, you are going to find really we are in a very good position now. I mean that the response is going to be better for us. A comparison of figure 3.22, which is the damped system, for damped system, and the undamped system, as you can see, shows that damping lowers each peak. Okay, damping lowers each peak and limits the response to bounded values. That's very true. We are going to have the bounds here. We're going to find that the bound that we have is going to be different, right? So here it is, the bounds are going to be like linear and non-stoppable. However, here we are controlled well. Okay. Let's go to the important influence of damping ratio on the amplitude. Okay, the amplitude itself. Let's examine the system, which is going to be for 0.01 damping ratio, 0.01, 0.05, and 0.1, and we are going to plot the same equation that already we have like derived before. Look here to this curve. As usual, horizontal is T over Tn. Vertical, it is the relation between the total response to the maximum static response. And we are plotting it for different values of damping ratios, 0.01, 0.05, and 0.1. Okay, that's the case. We are starting with initial conditions equal to 0, the displacement and velocity. At the initial condition, it was 0. Omega n equal to omega n. As you can see here, look to the damping, how it is affecting the response. Okay, this is actually under the sinusoidal force, as we have said. Look here, for the case of 0.05 or 0.1, look here, the response. I need to make it in a different color. Maybe here, this one is going to be good. Yes, here, look. It is like really damping everything. But look to the case where that we have 0.05 less damping ratio. You're going to find that the peaks are going higher every time, right? Look here, this is the case for the damping ratio 0.05. But look to the case of damping ratio very small, like 0.01, you're going to find that the peaks are higher and higher, right? So this makes us to be like cautious regarding the damping ratio. Whatever the type of damping ratio that you are going to introduce into your system, it is going to give you different response. So this is why we commonly say it's better for you to introduce some damping. Okay, higher damping for your system is going to guarantee for you that the total response amplitude is going to be within the limits. Okay, look here, for example, we are talking here for the case of 0.1, we are talking about almost like, let's assume 5 times or 4 times. But if we are talking about 0.01, it is something like 25 times. The amplitude due to the dynamic amplification is going to be 25 times the static amplitude. So this is very important example that we need to take into consideration when we are talking about the effect of damping ratio. This is the effect of damping ratio on the amplitude. Okay. Okay. Let's talk about the maximum deformation, and the phase lag. Okay, we're going to understand both of them in this in the coming few minutes. First of all, why we are going to focus on this? Because as designers, we need to take care of the maximum deformation. This is our main concern. Okay, what is the maximum deformation? And another thing which is related to the phase lag, I'm going to define it, and we want to know how much our response is lagging behind the forcing frequency, for example. I'm going to give the definition of phase lag and phase angle, but I'm going to place emphasis now from now on the steady state. This is our case now, steady state, because as I said, after that the transient will decay. If we go back to our equations, okay, and our graphical representation, we say that, as you can see here, the steady state is going to be always there after a while, but in the beginning it is going, the part which is transient is going to vanish. Okay, so we need to focus more on the steady state. Okay, from now on we are going to focus on the maximum deformation and the phase lag regarding the steady state response. So this is only something related to the title itself, that the steady state will be our focus from now on, because the transient response is going to be, or will, decay over time. Okay, as we have said before, our particular solution of this differential equation, which is already we have derived before, already we have done it, this is the particular solution, up of t equal to c sine omega, as we said, sine omega bar t plus d cosine omega bar t. So c and d, already I have explained them before. All the details of them I have given it before. This is c and this is d, and we have mentioned what are the parameters that is going to control these two constants. Okay. Now the point is, we want to put this equation, which is the particular equation here, we do not like, as I said many times, to put it in this form, which is sine plus cosine. It is not attractive for us, because we need to understand from the equation what is the amplitude and how it can be like changing with time directly whenever that we look to the equation. From the superposition of two sine and cosine, it's difficult actually to understand what is the amplitude and how it can be controlled. But if I'm going to put it in another form that is going to be attractive for us, it will be good if we can go with it. So look to here, I'm going to put it in this form, okay, which is going to be u naught sine omega t minus phi. Do you remember when I was like explaining this like a couple of videos before? We said that we have a kind of amplitude rho, and these two constants, they are going to be our c and d, and here this is the angle, we call it phi, and then we can represent this equation, okay, this equation we can represent it by substituting this rho underneath c and d and multiply outside and so on. This is already, I have explained it like a couple of videos before. So from here we can get a kind of equation that is very easy for us based on the response itself, which is this rho is going to be the square root of c squared plus d squared. Okay, this is the rho here. From this, the hypotenuse of this rectangle. So u of t is going to be rho times sine omega t minus phi. This is what we are going to have here. And this is actually our equation here. You're going to find in the textbook they used u node. So it is okay. U node or rho, it is no problem here. They are having the same understanding for us. Okay, there is no difference in this case. Okay. And here, as you know, this u node from the previous video, are going to find that it equals to what? U static node times RD. The maximum static response times the response modification factor. Right? This is what we have said before. And this u node, okay, as I said, u node, it is the same as rho. It's only different annotation, but they are like representing the same thing. So u node equal to the square root of radical of, or the radical of c squared plus d squared. And phi, this phi, it is the phase angle, for example. From this triangle, you are going to find that it equals to tan minus 1 minus d over c. Right? And substituting for c and d, this gives us the response modification factor. Again, this response modification factor, I explained it last time in the video, so please revisit the last video again. It equals to u node, which is the maximum dynamic amplitude over, or the u node, the maximum dynamic amplitude over the maximum static amplitude. You remember? So this is what we call it RD. And phi, from here we know already c and d, so we know this d and c. If we go back here, already we know we can substitute and get phi easily. So we can obtain phi easily. Okay, phi, it is the phase angle. Now we want to understand what is the meaning of this, why we need this RD and phi and this kind of stuff. Actually, it is important for us, first of all, to focus, as I said, on the steady state. So y or u particular is going to be represented by this nice equation here, by this equation. Okay, this is our equation. This is simple equation for us to understand. U of t equal to something which is amplitude, the dynamic amplitude, times sine omega t minus phi, where phi, everything in this phi. Okay, I mean that all the damping ratio, omega bar, and omega n. So we already like put everything in a nutshell into this phi. And then for this RD, it is very important to us, as we are going to see in the next video, how much this RD is important, because we need to always make a relation between the dynamic and the static. That's our concern. We need to know how much the dynamic response is going to be in comparison with the static response. We need to know this ratio. If it's like going to be 1, this means that we do not have any dynamic effect. But if it's going to be like 3, this means that the dynamic effect is going to triple the static effect. So we need to take care. We are going to have some precautions in our design. Okay. So now let's go to the point where that we understood what is the meaning of RD, but what is the meaning of this like phi? What is the meaning of it? Physical meaning. What is the definition of it? Okay, so let's go to the definition of the phase angle. Okay, so the phase angle, we can define it like this: the angle, okay, that describes the time difference between the system total response, we're talking about the system total response now, and the steady state response. Okay, what is the meaning? We said that we are going to focus on the steady state. Is there a kind of a difference between total response and steady state response? Okay, yes, you are going to find there is. I'm going to show to you in the next video that there is some difference. Even in the steady state, the forcing frequency state, or the response of the forcing frequency and the total response, they are going to have some different, like they are going to be lagging, or the total response is going to be lagging behind the forcing response, or maybe the opposite. It depends. Okay, so we can put this definition now. Okay, so for example, we are going to find that this is our total response, and maybe we are going to find that our forcing response is going to be something like this, for example. Okay, like there is lagging. Okay, our response is lagging behind the forcing response. That's the meaning. How we can obtain this is based on the phi, or the phase angle. As we said, we need to know how much this lagging is. So again, it is an angle that is going to describe the time difference. Other people, they define it simply like this. They are telling that it is the time by which the response, which means the total response, lags behind the force. Because we have force, right? We are having a forcing, we have force, which is P node sine omega bar t, right? There is like harmonic force is being applied. What about this harmonic force and the relation with the total response? The total response, maybe it is like lagging behind it, something like this. So we need to know how much this lagging is in terms of time. Okay, so mathematically we can represent this using this phi. Okay, this is regarding our video for today. I hope that you have understood everything for today, and I hope that you got the meaning of the phase angle, response modification factor, and the effect of damping on the resonance, and the solution of the equation of motion for the case of harmonic forcing equation on a damped system. Thank you, and see you in the next video.